Okay, so hi everyone. Welcome to the Quantum 2020 poster session 1B. My name is Kairys. I am the Executive Co-Director of PQI and a research faculty at the Chemical Engineering Department at Pitt. So for those of you who have attended our full poster session before, you may notice that the name is a little bit different this time. It was held part of the university-wide Science 20XX event, but that was put on hold indefinitely. Therefore, this year we launched this new Quantum 2020 event, which will be held in the future annually in the fall. And we're very happy to have three faculty judges. Professor Carl Johnson from Chemical Engineering Department, Professor Raul Hernandez-Sanchez from the Chemistry Department, and Professor Paul Odnicki from Mechanical Engineering and Material Science Department from Pitt. And one note for the judges is that we will have the recording of the event shared with you. So if you need additional time, you can finalize the score by Sunday night. And for the presenters, just a reminder, you have 3 minutes to present and another 3 minutes to answer questions. I will give you a note once you reach that time mark. But please stay after the talk to support and listen to your peers' presentations. And as you can see, some of the judges may not be from your area of expertise, which is by design. So please focus on making your presentation accessible to a broad audience. And without further ado, let's welcome the first presenter. I think it's Elliot. You're welcome to share the screen.
Okay, so my presentation is on controlling quantum transport in electron waveguides by periodic modulation. So the goal is, as is in the title, an electron waveguide is basically a nanoscale wire, and in these wires we have quantized electron transport. Now this is a theoretical work which is motivated by recent experiments which were done in Pittsburgh, where they apply a periodic potential in these nanowires that they create. And applications of this include quantum simulation, where you need this high degree of control over electrons. So the way we study these waveguides is we tune the chemical potential and we apply an external magnetic field B. And we look at the conductance of this, of electrons moving through this nanowire. And the conductance is the derivative of the current with respect to the bias voltage. Now, in an unmodulated waveguide, we see that this is quantized in units of E²/h. And what this means is that, well, basically, a single electron contributes E²/h to the transport. So if we see E²/h, we have 1 electron. If we have 2 E²/h, we have 2 electrons being transported, and so on. So we want to see how this changes when we add a periodic potential. And the simplest kind of periodic potential we can add is a chronic penny potential, which is essentially a square wave with an amplitude V0 and wavelength lambda. Now, traditionally, this is known to introduce band gaps into the band structure. And how we expect to see this appear in the conductance is that regions of zero transport will appear where there was transport in the unmodulated case. And we also include electron-electron interactions. And we suppose that the potential gradient engineers a spin-orbit coupling, which is essentially a mixing of the spins. And we want to see how this mixing of the spins affects the strength of the electron-electron interactions. So in the first case, we'll just look at the single particle transport. On the left is without the modulation, on the right is with the modulation. And now you can see these darker lines that are appearing in the plot on the top right. These are the regions that correspond to the band gaps in the chronic penny model. Now, if we have interactions in spin-orbit coupling, and we just suppose that the only effect of the potential is to engineer the spin-orbit coupling rather than having the potential itself. Then we, on the left is for small spin-orbit coupling, on the right is large spin-orbit coupling. Now the darker regions are the regions where the electrons are traveling as pairs because of the electron-electron interactions. And we can see that as we increase the spin-orbit coupling, the electrons, the region in the parameter space of bMu where the electrons are paired increases. So that's my presentation. If you have any questions, I'm happy to take them.
Okay, I've got a question. So how are the electron-electron interactions included? What level of theory do you use?
So we look at a contact interaction. As a first model, we're using mean field theory. We eventually want to use DMRG, but right now it's all of the mean field. So we have a mean field delta, which determines the pairing energy. And when this is positive or finite, that means we have pairing. And when it's zero, that means we have single particles.
Okay, so it's a mean field approach that you don't have like a Hartree-Fock approximation or anything like that.
Yeah, that's the kind of thing we do. We do the same kind of
so you do get Pauli exclusion from the Hartree-Fock, right? The Fock matrix.
No, we don't do a full Hartree-Fock, but it's the same kind of thing. We do it recursively. We have a guess that we put into the model, and then based on the guess, we get some output for our mean fields, and we plug this output back in until it converges.
Okay.
Elliot, in what kind of system is this model applicable experimentally speaking?
So Jeremy Levy's group in Pittsburgh, they do this kind of thing where they have LAOSTO. They have an interface of these two, and they write the nanowires as channels along this. And it's based off an experiment they did where they added a chronic pairing potential on top of this. The model here is an attempt to explain some of the features in this. The enhanced pairing is something that they do see in the experiment, and they see a fracturing of the conductance, which could be explained by the first plot.
So you mentioned that you use the chronic bending potential. Do you have any sense for how important the details of the potential are in this case? Do you think you've captured the essence of the physics, or do you think there are some other potentials that should be explored in the future?
So there are other potentials that should be explored in the future, and that's the direction we're going at the moment. We're looking at what happens if we do this chronic pairing modulation, but out of phase with just moving the wire in a sinusoidal motion along the interface, and that leads to some very interesting features that we're still trying to explain. But even on its own, this kind of sinusoidal modulation of the position of the wire, they see an experiment that this engineers is spin-orbit coupling. And the way they see this is that then, rather than having a single minimum of the conductance, it splits into two minima at around plus or minus B is equal to something like 5 Tesla. And that's a hallmark of spin-orbit coupling along the axis where they expect to see it.
Excellent. And we're right on time.
Okay.
So we can move forward. Well, thank you. Paul?
Yeah, I need Stephen to stop, or Elliot to stop sharing his screen.
Sorry about that.
No problem. All right, can everybody see my screen? Hello?
Yes.
Can everyone see my screen? Okay, cool. All right, so let me start.
Yeah, you might have to adjust your size. I'm seeing a portion of your poster here.
Oh, yes, I'm going to be moving through it.
No problem.
And then I'll zoom out at the end.
Okay,
that's all right. Okay, great. So thanks everyone for listening on this poster presentation on high performance quantum simulation through analog control optimization. My name is Kairys. I'm advised by Travis Humble at the University of Tennessee and Oak Ridge National Laboratory. So in this work, we're proposing a framework that uses quantum optimal control to design hardware level instructions for quantum simulation. We intend to validate this framework by simulating dynamics of the Bose-Hubbard model on circuit QED devices. It's important to note that due to differences between the device and the model Hamiltonian, it's not feasible to perform analog simulation. However, the framework we're proposing does not require any isometry between the Hamiltonians. To formalize the problem, we're using a standard technique known as trotterization to decompose the global unitary evolution operator into a product of local unitary operators. However, instead of further decomposing these unitary operators into quantum gates, we're using quantum optimal control theory to compile hardware-level instructions that implement these Trotter step unitaries directly. So we're using a recently developed algorithm called gradient optimization of analytic controls to minimize an objective function called infidelity over an analytic control ansatz. Our implementation uses an LBFGS algorithm to perform the actual optimization. As a demonstration, we use a sinusoidal ansatz along with amplitude constraints and time windowing to determine an optimal 40 nanosecond control field that generates a single site Bose-Hubbard Trotter unitary with infidelity 1 to -10. You can see that the pulse is relatively localized in the frequency domain, and we also show via the plots on the far right that the optimal pulse is relatively robust to finite precision. Moving forward, in conclusion, we're presenting a framework for quantum simulation that uses tailored analog controls to implement Trotter step unitaries, and we have shown a proof of concept simulation for a single site Bose-Hubbard model. Moving forward, we're intending to expand the simulation to multiple transmons and resonators and develop rigorous error estimates of this approach. And that's it. So let me take this back out. All right. So that's the overview of my poster, and I'm ready for any questions.
Why did you use 5 sinusoids? Why not 7? Why not 4?
Really, we found that we needed at least 3, but we chose 5 because the more basically this is the more basis functions that you're using, the easier it is to find an optimal control field solution. And so we found that 5 just worked well for the simulation. In any real application, you'd want to also minimize this so that you minimize the number of parameters that you need to calibrate when implementing these on devices. But we haven't done this for the proof of concept.
So aside from increased number of parameters as a disadvantage for having more functions, a larger basis set, is there a computational efficiency issue? Like, how does it scale with the number of basis functions? How does the calculation scale with the number of basis functions?
So the classical quantum optimal control algorithm scales linearly with the number of parameters. And so in this case, we're using 3 parameters per sinusoidal basis function. And so that means that basically we have 3 number of basis functions, and we have a linear scaling at that parameter count. It's still exponential in the size of the Hilbert space being taken into account. And so in practice, you'd want to optimize on, 2 transmon sites or 2 or 3 transmon sites, depending on the accuracy that you want to achieve and the error that your simulation can tolerate.
So can you speak a little bit to the selection of the lattice size in this case? How important is that? How was that selection made?
So, so in this case, we're considering a 2D lattice model Hamiltonian because the circuit QED devices that are available today are 2D planar architectures. And so really what we're able to do is we're able to take the fact that the transmon Hilbert space is isomorphic to a single Bose-Hubbard site Hilbert space. It's just basically a clock basis. And so we're using this kind of trivial isomorphism between the Hilbert spaces. And then we're just using the interactions that are available in the device to actually engineer the interactions that we're interested in, for example, in the Bose-Hubbard model. And so the choice of 2D, the choice of 2D lattice is just for convenience.
Excellent. In considering of the time, I think we have to move on. Thank you. And the third one, I think it is Berg. Do you go by Berg?
Yes, I do.
Okay.
Yes, I do.
Go
Let
ahead.
me go ahead and share
Floor
screen.
is yours.
Okay, is this all visible?
Yep, only the top part, but I think that's your design, right?
Yeah, I'll be scrolling through similar to the last one.
Sure, go.
So thank you for coming to my talk today. I will focus on our development of a reactive force field that models copper-nickel alloy oxidation, as well as surface segregation. This work is by myself, as well as some collaborators listed here under the advisement of Wissam Saidi and Judith Yang here at the University of Pittsburgh. Our motivation for these experiments comes from our copper-nickel oxidation experiments that are done within the transmission electron microscope. As you can see in these images here, there's a competitive oxidation between the two components within the alloy. They form oxides on the surface that are difficult to distinguish using XRD or even EDS mapping alone, given resolution limits. But the interplay between alloying vacancies and oxidation interfaces results in slightly tunable behavior based upon what pressure of oxygen you use and the temperature, as well as the starting alloy concentration, which hopefully would result in protection for active sites, as well as a tunable passivation process, a double layer passivation that could be arrived at if we know the atomistic mechanisms behind these transformations. Now, there's some differences between the TEM experiments shown here on the right and our models shown at left and in the middle panel here. The TEM experiments are visualizations of electron scattering through these pinholes, which are etched with hydrogen reduction in the copper-nickel alloy surface. So you can get these different facets, 1, 0, 0, 1, 1, 0, and so on. We can express these different orientations as surface slabs, as you can see in the middle. The surface slab models represent copper and nickel phase segregation at different steps along the process. Whether nickel is in the exposed surface, the subsurface, or the interior, oxygen still has an effect on the process, and we also model that with these slabs shown at left. Using VASP to perform DFT calculations to find the relaxed structures for these, as well as the ground state energies, we can show that the usual trend when there's a vacuum surface, or sorry, a vacuum atmosphere above the alloy surface, nickel prefers bulk sites that are more highly coordinated. However, when oxygen is introduced, the formation of nickel oxide bonds may be driving some of this nickel to the surface, particularly when oxygen is absorbed at a top site. We fit this density functional data to a reactive force field model. Now, ReactFF is a bond order parameterization, and we only vary a few parameters within this model: the bond, over coordination, and angle energies. This is a highly modular Python code that allows us, these red boxes are each individual classes that we can take out and use to transform parts of the optimization without affecting the overall process. As you can see at right, our Gaussian perturbation is what we're currently using, but it will in the future be updated to a genetic algorithm that can explore the state space, the parameter space, more quickly. As you saw at the bottom, our results for the, I see that. Results for the alloy surfaces are very good, the bare alloy surfaces. However, for the oxygenated structures, there's still some left to be desired, even though the relative energy orderings are correct. In the future, we hope to use this reactive force field to examine larger timescales more commensurate with our experiments. Thank you.
So what's the size of your training set in these, in your React's force field?
There are over 40 different structures that are involved here, and we're training to the surface energies of these structures.
And did you then test by trying to predict certain things? I guess, are these predictions, or are these on the bars here? Are those predictions, or are those actually fit?
So these are the predictions. The surface energies are what we would hope to model correctly. However, we're fitting to the relative differences between configurations that have the same number of atoms. Now, work on the code in the future will address adding new parameter types in the data import class within the Python code. So I'm working on that currently. So rather than just allowing projections, we could say these are actual fit parameters in the future.
This model is just thermodynamic. You wouldn't get dynamics out of it because you're not looking at like any movement of the atoms. Is that right?
It should, yes, correctly show the thermodynamic bond lengths between things, as well as the stable surface adsorptions. However, previous data shows that molecular dynamics force fields can be used to show dynamics of the long term, not just the thermodynamics. This embedded atom force field, which is the benchmark typically, has been used in the past for that.
So in terms of dynamics moving forward, what additional work do you think is going to be required to look at some of those questions?
So conventional MD scales that would use a reactive force field or an EAM force field can reach about many nanoseconds of time. However, there are accelerated MD methods such as parsplice, which is something that we're currently using with the vacuum state using an EAM force field that reaches the range of microseconds. Additionally, we would need more models for the 110 and 111 surfaces, especially since the 111 surface is not as clearly resolved in TEM experiments.
Okay, if there are no more questions, thank you. And I just want to point out that if for any students or judges, if you want to look at the poster, they're all available on a link, which I will post in the chat. And you can go back to there afterwards if you want to see the full poster again. Okay, our next presenter would be Omri. Did I pronounce that correctly? Hi, yeah.
Hey, just a second. Okay. All right. So my project is machine learning to accelerate screening for Marcus reorganization energies. So what I'm trying to find are candidates for conductive polymers with low reorganization energies. So reorganization energy is a term that comes from the Marcus theory, and it's related to the rate of the charge transfer. And it's also related to like the way that molecules change their conformation during this charge transfer. Theoretically, computationally, we can calculate this energy by calculating 4 different points for the molecule. But doing those calculations using DFT method can take a very long time, especially when you're dealing with long chains. So what we're trying to do here is to make a machine learning model to try to predict the reorganization energy for those conductive polymers. So my data set is a list of 253 different tyrosine-based monomers that give me a list of about 32,000 different copolymers and homopolymers. And from previous studies in the group, we saw that at the hexamer of the copolymer is a good estimate for the reorganization energy for the long polymer. So what I did here is to calculate the energy for the shorter oligomer. What we also saw that the reorganization energy for the tetramer has a good correlation with the hexamer, and because the tetramer takes less than half the time to calculate for to the calculation for the as for the hexamer, I went with calculating a list of about 7,000 different tetramers and about 400 hexamers to use as my training set for my machine learning model. My model itself, I used the random forest regression model. I saw it perform better than a neural network, and I fed it the 7,000 hexamers and the 400 hexamers to train it. And what I saw is this is the correlation plot between the trained and the calculated reorganization energies. And what I saw is that the trained reorganization energy is prediction is getting worse the higher the reorganization energy is. However, what we're trying to find is the lower end, where we have the lower reorganization energies and where we have a better prediction. So what I did is running the rest of the different copolymers and that I didn't calculate using DFT through the model, and then choosing the calculated, like the ones that have low reorganization energies. And so this model gives me like a good, like a first step screening tool to get a list of good candidates for conductive polymers. And the next step, what I'm doing now is to find the to find the DFT reorganization energies for those who I predicted. Yeah, and if you have any questions.
Let's see. So your training set is shown there, and what you're trying to find is materials with small lambda. Is that what you're saying?
Yes.
Okay. So in your, you could have like a false positive or a false negative. That is, your machine learning could predict something that actually has a large lambda as a small lambda, or it could predict something to have a small lambda that is a large lambda. Which is worse and why?
I would say the one that, well, I would say because we're trying to find something that has low lambda, like if it's trying to predict something that has low lambda, but it actually has a large one,
would that be worse than your model saying, or the model saying this has a large lambda and it actually has a small lambda?
Well, that's also true because it's a miss, right? We missed this polymer, and we didn't we didn't find it this model. But however, I already did some calculations on the ones that the ones that the model predicted, and there is a pretty good correlation already. It's very preliminary results that I got yesterday, but the model is pretty good. As again, like it's just a first step screening tool.
Omri, is there a common functional group in the monomers that lead you to the low lambda?
Yeah, so we see from the common monomers, we see a lot that has a nitrogen-containing heterocycles. Different heterocycles like 5 membrane rings, 6 membrane rings. The one that I see constantly give me a low lambda are the ones that is like a monomer that has a thiodiazyl group. So it's like 2 nitrogens and sulfur, 5 membrane ring.
So you talked a little bit about how the random forest model works better than a neural network approach. Mm-hmm. Do you feel that your machine learning model is a primary source of error, or do you think that what you're inputting is a primary source of error at this point? So I guess what do you think is your limitation with this predictive capability?
So the thing is, like the information I feed it is already like it's hard to predict the reorganization just by looking at the groups, and I see that actually the feature that the one that predicts the best correlation is actually the bond length between the different monomers, and so sorry. I lost my train of thought. So can you repeat the question again?
So where do you think your primary source of error is, right? Is it on the machine learning? Is it the selection of the machine learning model, or is it the input to the machine learning model that's more important to improve, to optimize this predictive capability?
Oh, so yeah, what I was to say, there's no one different feature that is a good predictor for the reorganization energy. This is why, like, it's a very hard question here to answer, because there's nothing, one thing that we know, like if the monomers have like a high pi system, like very large pi systems, it gives like low reorganization energies. It's not always the case this way.
Okay, thank you very much.
Thank you.
And the next one, I think, is Zachary. I think he joined us. Yes, good.
Yeah, a little late.
It's fine. Go ahead.
Okay, I'll share my screen. Okay. Can you all see my screen?
Yeah.
Yep.
Okay, great. Hello, today I'd like to talk to you all about my work on using multi-component metal-adenate MOFs for hydrogen CO2 separations. And slide over here. And the first thing I wanted to discuss is why we want to look at multi-component MOFs. These are MOFs that contain more than just one metal and one ligand. And the idea behind using multiple components is that you increase the kind of structural diversity in the types of products you can get when the MOF forms. Also, you have more tunable handles in order to optimize your framework for applications. So diving into this, we have this 4-component system, which is what we call bMOF 200. It has 2 different organic linkers. One is a pyrazole, which has a nitrogen functionality and a carboxylate functionality, and that coordinates with zinc to form these green cube octahedra cages like this. And then the other metal is a copper that is bound to adenine, which is our biomolecule, hence bMOF. And so these coordinate in a dimeric fashion, and actually 2 dimers stack perpendicular on top of one another to form this square shape. And then these come together to form this FTW net shown here. If we scoot over to the top here, I've shown the net, the MOF, as a function of its pores. So you can see the blue pores, the yellow pores, and the red pores are distinct, chemically distinct pore environments. And here we wanted to highlight the kind of different pathways that gases might diffuse through the MOF. So in one case, you could have from blue to yellow to blue, in another case, yellow to red, and so on. And so we wanted to try to take advantage of this for particular gas separations. And so using some theoretical assistance, we tried to model the diffusion of hydrogen and CO2 through the different pores located in the cage unit. And so this plot here shows the relative energy barriers as different gas molecules move through the opening from the empty space through the aperture shown at 0.0 and into free vacuum of the modeled system. And you can see that through the larger barriers, or through the larger windows, both gases can pass through relatively easily. However, in the smaller triangular aperture highlighted right here, only H2 is able to pass through that aperture with only minimal, with a minimal energy barrier. And then further, some energy binding energy simulations, we found that the CO2 prefers to stay within pore 3, the red pore, which is functionalized by 4 primary means. So what we did then is we submitted our MOF into breakthrough experiments. Okay. Breakthrough experiments, it showed good separation capabilities, better than other MOFs. And then we're also able to make membranes out of these and compare them to other MOFs and inorganic membranes, and showed very high selectivity and very high permeability. I'd be happy to answer any questions now.
How did you avoid pinholes in the membrane, which would then destroy the selectivity?
So we did multiple seeded layer, seeded growth approach. So we first formed our substrate and then grew some MOFs in a separate reaction, and then added them to the surface of the substrate, and then used those as seeds in subsequent growths in order to get a nice membrane. And we could monitor the removal of pinholes by increasing the number of steps for the growth cycles.
How many growth cycles did you use then?
For the bMOF 200, we used 5 growth cycles. For the isostructural MOF, which I didn't get a chance to talk about, 201, we actually only needed 2 growth cycles.
Can you talk a little bit about how the hydrogen CO2 separation factor compares to other MOFs and why you think this one ranks the way it does?
Yeah, so we believe that through our experimental and computational results that our MOF indicates both molecular sieving and competitive adsorption for the mode of separation. Some other MOFs, like this one up here, ZIF 100, is very selective and has a high selectivity factor due to very efficient molecular sieving. Both pores are designed so that it can thoroughly reject CO2. It's too large to fit through the apertures. So we do have a lower selectivity than those. However, our permeability is much higher.
Okay, if there are no more questions, thank you. And I think the next presenter is Stefan.
Yep. Can I just begin?
Yep.
Okay. Okay. So what we did was we wanted to make a physically motivated simple model for calculating the energies of temporary anions. Temporary anions are metastable states characterized by having a complex energy seen in equation 1, where the imaginary part of the energy is related to the expected lifetime of the state as seen in equation 2. Figure 1 here shows a potential that could give rise to a temporary anion. If the anion is in this state here, it will eventually tunnel through the potential, meaning it has a finite lifetime. So N2 minus is a temporary anion, and so we used equation of motion calculations on N2 minus using a basis set that had that includes some very diffuse basis functions. And we scaled the exponents of those functions, and we got this stabilization plot of the eigenvalues versus the scale factor. 2 of the eigenvalues come very close to each other in what's called an avoided crossing, where the discrete state couples heavily with the discretized continuum state. And this is the data points in orange are the data points we're using for our fit in order to calculate the energy, the complex energy. The normal way to go about this would be to do an analytic continuation of those points. However, we want to go about it in a more physically motivated way. So what we came up with was thinking about how this is just 2 eigenvalues, so we can think of it as a 2x2 matrix eigenvalue problem, where psi d is the wave function of the discrete state and psi c is the wave function of the discretized continuum state. We called E plus and E minus the 2 eigenvalues of this matrix. Then using the characteristic polynomial of the matrix, we can show equations 4 and 5. HDD is constant with respect to the scale factor because we're only scaling the diffuse basis functions, and therefore we're only scaling the discretized continuum and not the discrete states. So HCC, because of that, we can use equation 4 here to get figure 3, showing that HCC appears linear with respect to the scale factor. And then knowing that information, we can use equation 5 to get figure 4 here, which shows that HDC squared appears sort of quadratic with respect to the scale factor, or at least not more than just linear, a higher order than just linear. So then because of this, we came up with equation 6 here, where this is our model where the HDD is just a constant, HCC is linear with respect to the scale factor Z, and then HDC and HCD are squared is quadratic with respect to the scale factor. Then fitting the data to this model and calculating the complex energy, we get this for our energy, which is very close to what we get when using a 345 GPA or general Patti approximant, which is what would be considered a more exact method. So yeah, thank you for listening.
So are you taking the Patti approximate to be, quote, the exact answer?
Yeah, that's what we're taking to be exact. It isn't exact either, but it's kind of the best method for getting them at the moment.
Where's your biggest source of uncertainty? I mean, take a step back. The Patti approximate also uses your data that you started with.
Yes, it does.
So what's the biggest source of uncertainty in the whole model?
Well, so the biggest source of uncertainty, I would say, is the choosing which data to fit is the biggest source of uncertainty, because if you choose data, like if you choose like only data at the avoided crossing, you could miss other influences. So for instance, as you can see here, there's actually a second avoided crossing between these two eigenvalues off if we were to scale down further here. So if we chose only data like very close to this avoided crossing, we might not include, it wouldn't get that influence of that other avoided crossing. But if we went too far away, then we wouldn't get any of the mixing between the discrete state and the discretized continuum state. So choosing the data is the biggest source of uncertainty.
So what do you think is the most important motivation for this work?
So other than it being theoretically interesting, I think there are practical applications. So for instance, temporary anions do occur in nature, and certain chemical, and on the same time scale as certain chemical reactions, they can last. So if we can tell how long the temporary anion is expected to last for, we could make predictions about what chemical reactions it could undergo while it's a temporary anion, because like if a chemical reaction were to take like if its time scale is much longer than the temporary anions, we could say, oh, it probably wouldn't undergo that reaction, whereas other reactions it could do if it's around the same time scale or less. One example of that is actually CO2. There's some ideas for carbon capture of CO2, because CO2 can form temporary anions, but in order to do that, you'd have to react the CO2 minus with something that is on the same time scale as the temporary anion.
When you speak about a temporary anion, are you and you know you mentioned this being experimentally observable. Are you referring to like light reduction? Are you referring to chemical reduction, electrochemical reduction of a temporary or formation of an anion?
Yeah, it's just just reduction of a molecule, and but the electron will eventually tunnel out of the molecule. It will not stay on the molecule. So like N2 minus, it will, you can have N2 minus, but that will not last. The extra electron will only stay on N2 for a finite amount of time.
Okay, thank you very much.
Mm-hmm.
The second last presenter in this session is Xinyi. Thank you, Stefan.
Okay, hi everyone. I'm Xinyi from the Department of Physics and Astronomy. So today I will be talking about this experimental project, uniaxial strand effect on superconductivity in nanostructures at lanthanum-aluminate strontium-titanate interface. So we will break down the title backwards. So what is lanthanum-aluminate strontium-titanate? So this material, actually our first presenter, Elliot, has brought up, who's trying to simulate that. So it is 3.4 layers of lanthanum aluminate grown on the strontium titanate. So strontium titanate is one of the first oxide superconductor discovered, and the lanthanum aluminate is a semiconductor. So at the interface, we have a two-dimensional electron gas, and we can take an conductive AFM tip, apply a positive voltage to the tip, and move it across the surface. So we can create nanowires. So they're as small as 2 nanowires wide conductive channels on that. And those nanowires become superconducting when we cool it down to under 200 millikelvin. So this is a very interesting system to study because it's low dimensional. So one of my colleagues furthermore take it to prove that the superconductivity happens at the conductive channel edges. So this may possibly be a one-dimensional superconducting system. So we want to learn about the superconducting Perry mechanism. So this theory is still lacking behind. To do that, we introduce another factor, which is uniaxial strain. So we're able to apply stretch or compress the sample in one dimensional, and we are able to do it in cryogenic conditions. So if you look at the preliminary result, this result is performed at 50 millikelvin temperature. So this thing is superconducting to begin with. When after we apply certain amount of strain, say tensile stretch, the superconductivity is completely destroyed. And when we reverse the strain to compress, we see that the superconductivity is restored, and then it was destroyed again. So we are able to see that the strain changed the superconducting critical current continuously, and this it is superconducting and not superconducting. That these two phases are being changed back and forth with strain. So this is a very interesting result. And another thing is that so this set of result, we apply the strain in the direction that is parallel to our nanowire. But when we apply the strain perpendicular to the nanowires, we hardly see this kind of change in the superconducting state. So this is also, I think, is probably related to the low dimensional of the superconducting system. So this
3
is,
minutes.
yes, this is the current state of this project. We have some data. We're trying to look for theoretical explanations behind it, how to interpret the data and how it is related to the electron pairing mechanism in the system. Thank you.
Well, I'll try a question. I can't really see your graphs, but how abruptly does the superconductivity disappear?
Let me zoom this in so maybe you can see it better. If you focus on the first graph, so the y-axis is the amount of strain that is applied, and the positive one is tensile strain, and the negative is compressed. So when you, and this color is the current versus voltage. So it's a 4-terminal IV measurement. So when you see these kind of blue regions, so that is when the resistance is actually 0. So when you see that, that is a superconducting state. And this is accompanied by 2, red regions. So that's the coherence peak, also a feature of superconductivity. So when you see that, there is a superconductivity, and when you see you can see that changes, that disappears, that shape is different, and the minimum resistance is no longer 0. So I think it's a kind of a smooth change. It's not very abrupt.
Okay, so a follow-on question then. Would this thing just be moved to a lower temperature? You're already at a really low temperature, 50 millikelvin, but like if you strained it and then so that the superconductivity was like mostly disappeared and then cooled it further, would it reappear?
it's possible because the superconductivity disappeared may just mean that the transition temperature is lower than 50 millikelvin, which is when we measured it. Perhaps it's lower. We were actually not able to test it with our system because the fridge, the minimum temperature is 50 millikelvin, but that's possible.
Okay.
Can you just speak again very briefly on the mechanism behind the coupling between strain and superconductivity in the system?
So that's something we're trying to learn because the strain in the system is actually a relatively new experimental means at this cryogenic temperature. So we actually don't know much about it, but there is a paper that's published last year. They're doing experiment on strontium titanate. So it's the bulk strontium titanate material, and they apply the strain on it, and they saw that the superconducting transition temperature was increased by 50% when they apply enough tensile strain, and they see the critical temperature move down for the compressive strain. So that is also looking for explanation, and that is a three-dimensional superconductor system. And this one that we're looking at is two-dimensional, even maybe one-dimensional perhaps, at these conductive channel boundaries. So I would say that it's really lacking what is the mechanism. There are a lot of proposals, but not one really stands out as there should be a plausible theoretical explanation to this.
Okay, thank you.
Thank you very much. So the last speaker in this session is Tanya.
I'm here,
yeah.
Tanya.
Mm-hmm. Floor is yours.
Can you see my poster?
Yes.
Yes.
Okay, thanks. So, hi everyone. I'm from Chemical Department of Carnegie Mellon University, and I'm pleased to present some highlights from my current project entitled Machine Learned Fecal Theory for Orbital Study, which is in a collaborative study with a group from Los Alamos National Lab. So we know that machine learning is a powerful tool for computational chemists for nowadays, and it's many orders of magnitude faster than classic QM calculations. But why is it faster? Because machine learning methods directly predict properties bypassing the need for solving the Schrödinger equation. So what is happening inside the neural network, which is the main instrument of machine learning? So inside the neural network, it's happening multiple cycles of recognition of definite chemical environment features for each atom in molecule, and mapping those features with property of interest, like energy, charges, dipole moments, and so on. That is why basically machine learning models represent black box methodology, and their results difficult to interpret from the chemical point of view. I mean here that since these methods avoid the Schrödinger equation, they lack any quantum description of molecular physics. In other words, machine learning models do not capture the underlying physics of electrons and atoms. And that is a problem because for physically correct theoretical approach, we expect quantum description of molecular physics. And from the quantum chemistry, we know one incredibly simple method, which is known for its ability to capture quality physics phenomena occurring in molecular system. And this is extended Huckel method. Huckel Hamiltonian simplicity arises from using only two types of empirically fit parameters. The first one is the orbital energies on each atom, and the second describes electronic interactions and bonding between atoms. And so the main idea that by replacing these traditionally fixed parameters with dynamic parameters generated from the neural network, here we could expect many bonuses as to get the fast and cheap and quantum accurate tool for predicting chemical structures with capturing of underlying physics. And so how it practically looks like, you can see on histogram here of machine learned predicted Huckel parameters, and here we show just alpha values, so the atomic orbital energies. And it is surprisingly good to get the agreement between the machine learned and the original Huckel atomic s orbital energy for hydrogen. Why surprisingly? Because, okay, in Huckel theory, this parameter was taken from the ionization energy of hydrogen, like from experiment, which is 13.6 electron volt. And the neural network was trained just to reproduce molecular, but not atomic orbital energies. And despite this, it produces an average hydrogen s orbital energy of 12.5 electron volt, which is very, very close to Huckel, and this is very good for us. In the next slide, we'll make a step forward in trying to describe reactions. We show, next slide, that the dynamic Huckel parameters also correctly reproduce the changes in electronic structure in course of reaction. For example, CH bond stretching in methane molecule. And here you can see that both on figure B, both proteins successfully captured by the Huckel machine learned model opposite the classic Huckel Hamiltonian. That is obvious lack of Huckel Hamiltonian, which can be used for reaction studies. And this is clearly shown on figure A here, precisely because of exploring fixed parameters showing in dashed lines. In contrast, machine learned Hamiltonian capture changes in atomic and hence in molecular orbital characters in course of reaction, and those characters are definitely not constant, as you can see on these figures in bottom. So what we basically work on is characterization of division of labor between machine learned algorithm and physics aware algorithm, like Huckel Hamiltonian here. And we see that dynamic parameters are smooth with regard to geometry change, even as complicated orbital interaction occurs. And I hope that we are able, and in the beginning of generating highly synergetic relationship between machine learning and physics model, which is hard but possible, and this will result in fast, cheap, interpretable, and physically correct theoretical approach. Thank you.
What's the upper limit of accuracy on this? So you're using this Huckel method, and I mean, how would this? You're not training it with DFT, are you? I didn't quite understand.
Sure. So we trained against DFT values of molecular orbital energies and some density functions. Okay. But we got them from DFT, sure.
And so, could you ever approach DFT accuracy?
We are yes, sure. The neural network, which is trained on DFT values, approach DFT accuracy, and it's because those values collaborate very nice.
Okay.
So
maybe so I'm understanding your figure, but your figure looks like the DFT results and your results are quite far off. And that, yeah, that figure like D or something, where the dashed and the solids, right?
Say it again, please.
Like this figure here, if you zoom in, the dashed lines are from DFT, the solid lines are from your model. And it looks like they're really far off.
Here, for example, here, yes, here's dashed line are DFT, and they're reproduced very, I mean, I see very nice.
I guess, and I'm looking at A, D, and E, where they don't look so good.
This don't, for me, they looks good. Why? Because these are, by the way, this is orbital occupations, and it reproduces how the occupation changes in the route of reaction. We do not expect here to reproduce in bottom figures to reproduce exactly the occupation values. We expect to reproduce the shape, I mean, the physics. And here I see that the physics is reproduced very well. These red lines are for the atomic 2s for carbons, and we have here some errors, but the physics is correct. And here, what is most important here is molecular orbital energies, and with our calculations are in accordance with DFT values, and it's very good. So, but using ML trained Hamiltonian is much more faster, and it can be used for reaction study instead of classic Hamiltonian, of course.
can you get electron densities out of this method?
Yes, sure. So because basically we use just some parameters from neural network, but after we solve Schrodinger equation with this with Hückel-Hamiltonian, so we can get all the information about electronic structure and the density, electronic density, of course. So that's the point, that we want to open this black box and look inside and extract some physics-aware information about the electronic structure, but make it faster and with critical accuracy.
Any other questions? If no, thank you very much. And thank you all for the judges and students who presented and judged in this session. That brings to the end of this session. I just want to remind you all that there is still another session happening in the next hour from 4:15 to 5:15. And in the link I put in the chat, you can find the room number, the Zoom link numbers. And just like a actual physical poster session, you feel free to join any of the sessions that you find interesting, and a complete list of the posters and the actual poster themselves are available in that link as well. Thank you.
Thanks, Ke.
Thanks.
Thank you.